let's start today's class. Today we'll be talking about GPS survey method, and this should be very useful for you for your PhD purpose. I think if you are planning to use GPR, then this will be very useful for you. So GPR survey mode or any survey mode can be for GPR or seismic. The survey mode can be divided in on three types. So first one is the reflection profiling, just like the Wiener profiling. What we generally do for the profiling, we generally map or image the subsurface up to a fixed depth. Suppose 10-meter depth, your target is at 10-meter depth. So you will be surveying up to 15-meter depth, and that 15-meter depth will be constant. So this is the survey line at on the top of our surface, and this is the maximum depth of penetration. Okay, so that's called the profiling. Second one is your sounding. You know about the sounding, that you will keep for the sounding. In this case, you have to take the transmitter and receiver a bistatic configuration. Without bistatic configuration, you cannot use or you cannot do the sounding technique. So this is your middle point, observation point. So initially you will keep transmitter and receiver here, let's say at 10 centimeter distance, and this is for 10 centimeter distance. Okay, so suppose that's the boundary. So what will happen? This will go like this. After that, the transmitter guy will move backward and backward by 10 centimeter. Let's say this is a 10 centimeter. I'm not drawing it properly, and this is, let's say, the 10 centimeter. So then again it will move 10 centimeter from the previous position, and it will move 10 centimeter from the previous position, like this way. And in for the next position, that will be your ray path from this to this, from this to this, then from this to this. So for the second position, that will be the ray path. For third position, that will be the ray path. That's why at this location you are having a 1D data, 1D information of several layers. And generally the CMP, it is called the sounding or the common midpoint survey. Common midpoint survey, that is CMP. So in CMP the data will be looking like, so for the reflection profile, if you see the data, this side you will be plotting time or depth, and this time your offset. Offset means from starting point to the distance is covered, and the distance has been measured using that calibration wheel. Sometimes you have this calibration wheel, this one. Okay, so this wheel has a function to measure the distance, just like the odometer in odometer, or yes, the odometer or the distance measurement unit placed in a motorbike or any car. Okay, same fundamental principle will work here to measure this offset. And offset you will find several high amplitude reflection, several low amplitude reflection, and you will have a 2D cross section. But from the sounding, if you want to know the velocity of the subsurface, because velocity is will be very useful. I have to ultimately, when I am producing a result, that result should be of depth. And how do you but you are having here the result of time, 2A travel time, that is T, let's say it's a nanosecond, and that X is the distance, offset distance. Now the result I have to produce is T. So how do you find D using from T? D will be equals to VT, velocity multiplied with time. So that's why velocity is very required. For this reason, we generally first do the sounding at a point, and then we find out that, okay, suppose I am surveying at a coastal region or a fluvial region, and there is 4 or 5 layers at the subsurface up to 30 meter. So at first I'll be doing the sounding, that is the common midpoint survey, CMP. And this CMP, after doing CMP, will have the velocity of different layer. So this layer velocity you know, this layer velocity you will know, and this layer velocity you will know. After knowing the velocity, you will be multiplying with time, and it will be modifying, or it will give you the depth. Okay, and generally as it's moving from moving away from each other, so the CMP curve will be looking like, if I draw a CMP curve, that CMP curve will be looking like this. This is how a CMP curve will look like. This is the for the closest distance, and then this will be the second point, this will be the third point. This is how a CMP and data will look like. Okay, so GPR investigation we can classify. I think I have told you that it can be classified data acquisition and processing. Acquisition and processing both have a acquisition, processing, and interpretation. Both are it's individual a subject. Okay, so acquisition is different. I mean, uh, during our MSc, we read the processing of seismic data in one semester. Like you were reading, you were studying for 4 credit. We used to study 4 credit for the only the processing, and 4 credit in the next semester for the interpretation. Okay, so it's a huge topic, but I'll be presenting this is a concise manner. So this hyperbola you are getting, this is for CMP survey, and this is for your profile. Not this is also for CMP survey if you are taking one side. Okay, there are several things are there. I'm not explaining it. So data acquisition, after data acquisition you will having this raw data, and which is not visible, the underline or uh, the features are not visible in this image. So the image processing technique or the GPR data signal processing technique we have applied, and after processing, after certain processing, we get this data. So raw data is not clearly visible. So you have to remove the unwanted noises, and then you have to find out. The after processing, you have to do the data interpretation. Interpretation done by the qualitative analysis or the quantitative analysis. I have already given you the example that he is better than her. How he is better than her? That is the how much he is better than her. That like he scored 10% better than her. Okay. So if I say he is better than her, that is the qualitative statement. If I say that he is 10% better than her, then it is the quantitative analysis. So for the qualitative analysis, by seeing the structure or by seeing the reflections, we uh, generally interpret as a that this is a coastal dune or this is a channel. Okay, that's the qualitative analysis. Now, if I go for the property or the dialectic property of that part, that will be the quantitative analysis. Okay, so first let's talk about the GPR data acquisition. GPR data acquisition, as I was saying, it can be divided in three mode: reflexive profiling, velocity sounding, and transillumination. Reflection profiling, the same principle. I have already discussed that. Same analogy I have given to you. So there is a well, and in this well there is a water at a depth. How do you understand how deep this or at what depth the water is located? What you will do, you'll be throwing a pebble, and by listening the sound, impact sound, and the time it's taking, you can say that, okay, this water is at mark depth, and this is at a shallow position, or this is at a deep position. Similar analogy has been applied in this technique here. Let's say this is a different layer, first layer of different dielectric constant and different conductivity. Let's say this is sigma 2 and epsilon r2. This is totally different layer. So layer 1 and layer 2, and this is the boundary of layer 1 and layer 2. What will happen? The layer, this GPR signal will be reflected from this boundary and will be received at the receiver position, and this is how the um, reflection profiling is done. Okay, several parameters are there you have to consider before choosing the or before going for the surface. The operating frequency, which frequency will be applicable for you, that you have to understand. Suppose you are doing for an archaeological survey, and there is a thumb rule or there is a thing that mostly all the archaeological survey, archaeological materials are within 5 meter of depth. So I have a depth of penetration very low, but for the archaeological thing, we have to go for high resolution um, condition. So for the high resolution condition, which type of antenna giving you the high resolution condition, lower frequency or higher frequency? It's the higher frequency. So higher frequency antenna will be going for the higher resolution. So I'll go for 400 megahertz or 600 megahertz or your 200 megahertz. Below that, I will not suggest you to use. Okay, but if you are going for the water table delineation and the water table has 30-meter depth, 150 feet depth, then what you will do, or 100 feet depth. So what you will do, you will go for the lower frequency. It will give you low resolution, but it can identify the water table depth. So that's are the criteria. That's are the frequency criteria you have to choose. First, you have to understand the where could be your target is. What is your target? Okay. According to your target, you have to choose the antenna, and then you will be doing the study. So for the sedimentary study, I will suggest you to go for 50 or 10 to 500 megahertz. Sometimes due to the moisture content, the boundary layers can be identified, or due to the unconformity, you know about the unconformity, this can be identified easily on the radargram. Radargram means the radar signal or the image produced by the GPR survey. Okay. Next is the step size. Step size means the station spacing. I told you here that in the sounding, let's take as a 10 centimeter you are taking. And then again, after 10 centimeter, transmitter guy will move away from the receiver guy from the previous position, and it will move away from the previous position 10 centimeter. And this 10 centimeter I am taking every time is called the step size. It's an important topic. Step size, or one thing you might know about the station interval. So this station interval should have been chosen according to the frequency also. Okay, so there is a frequency called so there is this frequency, let's say it's a 80 megahertz. Okay, then transmitter receiver distance you have to maintain minimum 1 meter. That's the thumb rule, or that's the manufacturer decided thumb rule, you can say. So this told us, say you have to keep transmitter receiver separation at 1 meter if you are going for 80 megahertz antenna. That's the one point. Okay, so this step size is very important, and then you will be doing the survey. Suppose you don't have much time and you have to cover a whole lot of area, then you will be go for larger step size. So if you are taking instead of 20 centimeter instead of 10 centimeter, then it might not give you the good result as 10 centimeter, because as closely spacing you are taking, it's a simple concept. If you are taking data, suppose if you are taking data closely spacing, that can help you to draw. Suppose this thing you have to draw, and you have taken closely spacing data, then you can draw like this. If I'm connecting the dots like this. Now if you take the dots like this dot, I'm taking that, you are taking the spacing dot, one, then this one, then this one. Then how do you draw it? You can draw like this taking thing, or this taking method is called the sampling. This is the thing is called sampling. Okay, so when I'm doing the coarse sampling, coarse means I'm taking the spacing, this interval between these 2 point or two station is called station interval or step size. So by taking closely spacing interval, it will take much time because you have to take every time the data, but it will give you good result. But in this case, as you can see from this example, this is not for the GPR, this is a common sense example. So here you can see the curve is like this, but you are drawing like this in the core sample because you have taken 3 data instead of 16 data. Okay, so that's why the station interval and the step size aliasing, there is a Nike's formula is there that should be followed. the sampling interval. So in sedimentary studies, maximum step size is 1 meter. So to delineate the feature, to delineate the sedimentary feature, don't go for larger step size. So we'll be going for 1 meter. And larger step size where you can say when there is a horizontal layer, like a sand layer, horizontal succession of sand layer is there, then you can go for larger step size. For cross stratification, so if you are going for the cross bedding delineation, you will be requiring 0.2 meter station interval. That can give you, or that can be only useful for mapping the subsurface. Okay, so this is very important part, step size. Now length of the time window, this is another thing. So here the time window length will be how do you be choosing how far you will be recording, like the time signal you have remember from the time signal, and GPR is exactly based on the time signal, time formulations. And how this works actually, this works generally, and how long you are taking. So suppose that your duration is, let's say your duration is, you are taking a large duration. So what will happen? I'm plotting it here. So you have taken, let's say you have taken 700 nanosecond. Okay, from 0 to. So and you are having data up to this. So your data will be on the on that screen. It won't be visible. So your data will be, and the rest of the data. This is the noise part. Okay. So this part is your data, and this can be removed, or this portion can be removed easily. Okay, there is a technique, but I'll suggest you, if it's going for the 400 nanosecond, then you will go for, I'll show you an example. I will go for the 500 nanosecond. That is the maximum depth of penetration of the GPR signal, and you are taking somehow somewhat or 450 nanosecond, so that you can get this maximum depth of penetration. Now if you take less or if you fix the time duration less, then what will, if let's say you kept the time duration 350 nanoseconds, then you are losing this much of data, and once you came back from the field, that will be very difficult for you to go again and do the survey. So during the survey, you have to keep in mind about the time duration also. Then the time sampling interval, similarly to the station interval, is there. Read it. Antenna separation, what should be the antenna separation? Like 80 megahertz, you have to keep the antenna separation 1 meter. For 40 megahertz, you have to keep the antenna separation 22 meter. And generally you have to go for the, if you are doing the sounding, then that you have to go for the target depth by 2. So suppose your target depth is 10 meter, so your antenna separation should be 20 meter in case of CMP method. Okay, or in the reflection profiling method. I'm talking about the reflection profile. So antenna separation should be target depth by 2. That's the thumb rule. Then line location, antenna orientation. For water table condition, we generally take the PLBD broadside condition, and this or this saying on this technique, not this technique. These things are way advanced. This was from a old theory of GPR, but now the instrument or commercially available equipment, you don't have to do anything. First, you set the data, and you can do the survey. And survey, you can do a survey in a 2D manner like this. You take one line and one line like this. So this will give you one profile of GPR. This is another profile of GPR. You will have radiogram. So this will give you one radiogram, second radiogram, third radiogram. And for 3D survey, we will be taking the cross direction also. So this is the called the inline direction. I generally take the long direction or long. So suppose there is a rectangle, and this area you have to survey. So this direction will be the inline direction, and if you take the data from this direction, that will be the cross line. So this is the cross line, and this is the inline. Okay, remember that. A whole lot of things are there. Generally, what you have to do, this is from GSSI's control unit. Okay, control unit screenshot, and you here you can see this is how this you have to treat. This is 400 megahertz. You have to specify transmitting rate. You have to specify mode. You have to specify, and then samples, format, scan, several lot of parameters. You have to fix it. Then you will be doing the survey. You will be good to do the survey, and this could be the raw data. This is the raw data. Okay. So this is the direct wave. First, you will have the direct wave. How the direct waves are generated? From the FD theory, you know that so transmitter and receiver, transmitter to receiver is going. That will be the direct wave, and one will be going through or from the target. That's the target. So transmitter to receiver is called direct wave. After that, so it will be reaching AGR, it will be reaching earlier than this wave, that is received reflection, and that will give you the idea. So this will be the boundary. So when I will be choosing a time window, see how they choose it. They choose the time window. They kept some on the top side and some on the bottom side. That I will show you. Wait. Next is velocity finding. That's called the CMP method, common midpoint method. And this common midpoint point, that's the first position. One means the first position. Okay. Then you will be going for this. The transmitter will be in the receiver will be in the second position. Transmitter will be in the second position. Okay, that will give you another data and third position. And the CMP data, there is CMP data generally looks like the reflection. CMP data generally looks like if this is X and this is T, T means the two-way travel time. The CMP data will be looking like this. Okay, I mean, and the traces will be okay for obvious region. If you are increasing the transmitter and receiver distance, the first arrival will be late. If you are increasing, suppose and initial position, this is the transmitter receiver distance. So the signal will or the direct wave will be reaching at the receiver. Direct wave means the signal coming directly from the transmitter to the receiver, not via subsurface. Okay, so it's the direct wave, and direct wave will be reaching that. Suppose it will take 1 nanosecond. If you kept make the spacing now for the second position, that is the transmitter receiver position, then it might take, or for obvious reason, let's say it's taking 2 nanosecond. The time will be taking more, or they will be taking more time for the wider spread than the narrower spread. It's a common concept. Okay. And then transillumination surveys there. So transillumination surveys generally do in the borehole for engineering and environmental studies. This is also a famous GPR investigation, and it could be done transmitter receiver like this. So there are several transmitter will be put here, or you can do two things. One transmitter, one receiver coil is there. We generally used to do this method in the downhole seismic condition. So you have two borehole. It's called the cross hole technique. What technique it called? It called the cross hole technique. So two borehole you have, and then you will be putting transmitter here by a cable, and then you will be putting receiver here. And in that cable you have the depth marking. So in that marking you see that your transmitter is supposed at 100 meter, or let's say for sake of simplicity, let's say it in 50 meter. Okay, and it is also in 50 meter. Okay, now after taking the data, so this transmitter will transmit, and this in between the in between, whatever the subsurface materials are, this material will be mapped. So this portion I have highlighted, this portion will be mapped using this technique. Now what I will do, I will pull it up. I will pull it up again, and I will keep you this one as 45 meter. For the second position, I'll be keeping transmitter as let's say 45 meter, as a 50 meter, and also I'll be keeping receiver as 45 meter. Then what will happen, this portion will be mapped, and okay, By doing so, you will be having the whole idea of up to this portion. So this whole data, so this whole area will be mapped using this transillumination technique. It is also a famous borehole GPR technique. It's called the borehole GPR. Then a zero offset profiling is there, multi offset profiling is there, whatever you want. Now, 2D bi-static common offset reflexive data, these are the steps and these are the objectives. So, how frequency noise, how would you remove high frequency noise using vertical low pass filter, horizontal low pass filter? So, it's itself a huge chapter. Like migration has a huge chapter of 200 pages, okay, generally. So, I'll be not going for that. What are the softwares of GPR? That is Reflex W. That's for your knowledge. Redan 7. I have worked on a Redan 7 software. Then GPR Max, GPS Slice. GPS Slice is another software. Okay, open source software. Now, GPR data interpretation, I talked about the quantitative interpretation. In the quantitative interpretation, there is a term called the full waveform inversion or the rate tomography. Both are there. So this was from my PhD defense slide, and here you can see that rate tomography is not mapping. So this is the true model of permittivity, true model of conductivity. This circular thing. This thing by modeling you can go up to this part. This accuracy by full waveform inversion, like conductivity like this. See that after modeling